All right, everybody. We are in 6.5 now. Properties of logarithms. So much more properties of logarithms. More than 6.4, right? Okay. So the first page is all about log properties. So in the properties given, m, n, and a are positive real numbers where a does not equal 1 and r is any real number. Okay, so look at the first log properties. It says log base a of 1, meaning the log can be any base it wants, but no matter what, the log of 1 is always 0. And the same can be said for the natural log of 1. If you type these in the calculator, log of 1, natural log of 1, no matter what the base is, will always be 0. Okay, so I could say log base 5 of 1 would still be 0, no matter what. Okay, and then next one, log base a of a is equal to 1. So if the base of the log is the same as the number you're taking the log of, then they will cancel and leave you with 1. Same goes for the natural log of e. The natural log of e is 1 because the base of the natural log is also e. So, good example of that. Let's say you had log base 2 of 2. These would cancel and give you 1. Yeah. Next is a raised to the log base a of m will equal m. So this base of a, if this base, exponential base of a, is same as the log base of a, then the exponential and the log will cancel and leave you with m, the number you're taking the log of. Same goes for e and the natural log. So e raised to the natural log base e of m, since they have the same base, they'll cancel and leave you with m. All right, well, that's another good example of that. Let's say I had, I'll just keep it 5. 5 raised to the log base 5 of m. Since the bases are the same, that 5 and that 5 are the same, they cancel and leave you with m. Okay, perfect. And then the next one builds off of the second property. I guess I could label these, right? Property 1, 2, 3, and 4. This says log base a of a raised to the r will leave you with r, which builds straight off of this. Log base a of a is 1, and then those will cancel and leave you with r. Okay, and again, same thing goes for the natural log. So good example, let's say I had log base 7 of 7 raised to the r. Since these are the same, they cancel and leave you with r. There we go. All right, not bad. So these are some basic log properties. And one of the easiest ways to remember these is just throw them in a calculator if you need to. Okay. Bless you. All right, now on to the 3 most important log properties you're ever going to use, you're always going to use in the future math classes. The product to sum, the quotient to difference, and the power rule. Okay, so let's look at how the product to sum works. Here, if you have log base a of m times n, this means that the product inside a log can be split into the addition of 2 logs or multiple logs. So log base a of m times n can be split into log base m plus log base a of n. So however many terms are in the parentheses in the argument of the log is how many times you can expand the log. And the same can be said for the natural log. The natural log of m times n is the natural log of m plus the natural log of n. So this is the product to sum rule. All right, what's a good example of that? So I could say log base 2 of xy becomes log base 2 of x plus log base 2 of y. Okay, and remember that these can also be reversed. So you can take log base 2 of x plus log base 2 of y and put it back as a single logarithm. So these work back and forth. So log base a of m plus log base a of n can become log base a of m times n. So you can work these both ways. Same with the natural logs. Okay, so that is the product to sum. Next is the quotient to difference. Log base a of m over n becomes log base a of m minus log base a of n. So the quotient inside the logarithm can be expanded as a difference of logs. And the same can be said for the natural log. Okay, what's a good example of that? I could say natural log of, hey, let's do 5 over 4. Why not? I can write that as the natural log of 5 minus the natural log of 4. Good times, right? All right, and once again, these properties can be reversed. So you could take natural log of 5 minus natural log of 4 and rewrite it as natural log of 5 over 4. Okay. Bless you. And then next one is the power rule. Simplest rule for logs. Log base a of m to the r equals r times the log base a of m. This means that all you do is take this power and bring it to the front. And you get r times log base a of m. The same with natural logs. Natural log of m to the r, this r comes to the front and gives you r times the natural log of m. So I could write log base 5 of x to the n, and by the power rule for logs, this would become n times log base 5 of x. And once again, all of these are reversible. So you can start here at n times the log base 5 of x, take that n, put it back on the exponent, and you'll get back here. Okay, so like I said, these 3 log properties are the most important log properties. These are the ones that you'll use in Cal 1. These are the ones that you'll use in Cal 2. These are the ones you'll use in pre-Cal. Sorry, I skipped pre-Cal. Okay, so just remember these 3 log properties. Like I said, the ones above, you can just easily type into a calculator and figure out. But again, you don't have to use a calculator. You can just remember these properties. But these 3 are way more important than the ones above. Okay, so let's go ahead and simplify these log expressions by using the properties we just learned. Okay, so first one, log base 2 of 2 raised to negative 13. This base is the same as this base, so they will cancel, right? This one uses that one property, log base a of a to the r will equal r. So log base 2 raised to the 2, log base 2 of 2 raised to negative 13 just becomes negative 13. There it is. You can even use power rule on this. You could say log base 2 of 2 raised to negative 13. And by power rule, that negative 13 would come down. And you'd get negative 13 times log base 2 of 2. And this uses the property that log base 2, that log base a of a is equal to 1. So this would become negative 13 times 1, which gives me negative 13. So many ways to solve a logarithm, right? The third way, like I said, plug it in a calculator. Okay. Natural log of e raised to the square root of 2. This uses the property natural log of e to the r will equal r. It's the same property that we use above. So this means that the natural log of e to the square root of 2 is just going to be the square root of 2. Or, once again, we use power rule. You can say natural log of e to the square root of 2 becomes square root of 2 times the natural log of e. And based on the properties on the first page, the natural log of e is 1. So here, you'll get square root of 2 times 1, which gives us square root of 2. My goodness. Logs are crazy, just like exponentials, right? Okay. C, e to the natural log of 8. This is going to use that property that e to the natural log of, we'll just say e to the natural log of m will give me m. So this means that e to the natural log of 8 will just give me 8. All right. And there's no other way around that one. There's no other way to solve that one. Okay. Hey, you did it. You're trying to escape. I see you. All right. So next is log base 6 of 9 plus log base 6 of 4. So what we're going to use on this one is the product to sum rule, but we're going to use it backwards. So for this one, we're going to say log base a of m plus log base a of n, which is what we have, and we're going to put it together as one single log base a of m times n. So that's what we're going to use here. So that means that this becomes, so I rewrite it, log base 6 of 9 plus log base 6 of 4 becomes log base 6 of 9 times 4, which will give us log base 6 of 36. Oh, but we are not done, y'all, because we can simplify this further if we write 36 as a base of 6. So we can rewrite this as log base 6 of 6 squared, And by log properties, since this base is the same as that base, our answer here is just 2. Crazy, I know. All right, this one uses that property again. Log base a of a to the r is equal to r. Okay. Next one, E, is going to be the quotient of difference, but we're going to work it backwards since it's already a difference. This one's going to use log base a of x minus log base a of y, and we're going to put it together as log base a of x over y. Okay, so with that being said, log base 8 of 16 minus log base 8 of 2 becomes log base 8 of 16 over 2. And now we can reduce more because we know that 16 over 2 is 8. And now this base is the same as that base, which means that by that log property, we're just going to get 1. So this used log base a of a, which is 1. You are crazy. You got it. All right. Let me do this and then I'll put the baby up. Okay. So now we have 5 raised to log base 5 of 6 plus log base 5 of 7. So what we're going to do is handle this first. We're going to have to put this into one single logarithm. So once again, this is going to use that log property, log base a of m plus log base a of n equal to log base a of m times n. Okay, so that means that 5 raised to log base 5 of 6 plus log base 5 of 7 becomes 5 raised to log base 5 of 6 times 7. Okay. And then you get 5 raised to log base 5 of, what is that, 42? And by our log properties on the first page, this base is the same as that base, so it cancels, and we will be left with 42. So this one used a raised to log base a of m is equal to n. Look at that. So that's how you use log properties, y'all. And we're going to keep doing it today. It can get a little crazy, but just try to keep it simple. Okay, no more baby. Let's keep going. So now these examples, we want to take the logs and expand them. So by our log properties, this first one is going to use the quotient to difference. So we see that you have a quotient on the inside. So now this will become log base 3 of x, oh, come on, minus log base 3 of 9. And now we have to simplify this more because you can write 9 as a base of 3. So that means that this becomes log base 3 of x minus log base 3 of 3 squared. And since the bases are the same, they cancel and leave us with log base 3 of x minus 2. There we go. Okay. Now, for B, log base 7 of x to the 5th. This one's easy. There's only one term inside the log, so we don't have to expand it. All we have to use is power rule. So we take this 5 and bring it to the front. So this means that our answer for this one is just 5 times log base 7 of x. And there's nothing else we can do there. Thank goodness, right? All right. Next one, it's going to be another quotient to difference using the natural log. So this will become natural log e minus natural log x. Okay, but now from the very first page of properties, the natural log of e becomes 1. So you get 1 minus the natural log of x. Done. Can't do anything else there. Okay. Next one. Again, this is going to be a quotient to difference. So this will expand to log base 2 of a minus log base 2 of b squared. And we can expand this one more time by using the power rule, because we see that this 2 can be brought to the front. So our answer, final answer, will be log base 2 of a minus 2 log base 2 of b. Okay, perfect. Let's keep going. Ooh, look at this one. Now we're getting to complicated stuff. Okay, so now we want to expand this logarithm. So inside the log are 2 terms. Out here is just telling us the domain that we have to abide by. We're not plugging numbers in, but it's just there to show us, hey, if you were to plug numbers in, you know that x has to be greater than 0. Whatever x values you input would have to be greater than 0. But like I said, we don't have to worry about that because we're only expanding this by log properties. So now this is going to use the product to sum, because we see 2 terms multiplying each other. So when I expand this, I'm going to get log base a of x plus log base a of the square root of x squared plus 1. Okay. But we can go one further step. We can rewrite any radical as an exponential power. So what we're going to do with this one is that the square root of x squared plus 1 is the same as x squared plus 1 to the 1/2. So that's what we're going to use here. So can't do anything. Can't do anything for log base a of x, but we can rewrite the square root as x squared plus 1 to the 1/2. Now, we can apply power rule, which means this 1/2 is coming to the front of that log. So we are going to get log base A of x plus 1/2 log base A of x squared plus 1. And we can't go any further with this one. If you're thinking you can expand this one more, we can't, because those two are connected by addition, which means we can't expand anymore. If they were connected by multiplication, then yes, we could. Okay. Oh boy, look at that one. Okay. So to start with, we have the natural log of all of that raised to the 1/3. So the first thing we're going to apply is the power rule. So this 1/3 is coming to the front. So we're going to have 1/3 times the natural log of all this, x squared minus x minus 2 over x plus 4 squared. Okay, and now, since there's a quotient on the inside, we can go ahead and expand this as the quotient to difference. We have to be careful with that 1/3 though. So the way we're going to write this is 1/3 times the natural log of x squared minus x minus 2 minus the natural log of x plus 4 squared. Okay, and now we still have a lot of cleanup to go. This part, I believe, can be factored. So let's see what happens there. You get 1/3 times the natural log, and this factors to x minus 2, x plus 1, x squared, x negative 2, good. Minus, and now on this one, you can apply the power rule. That 2 can go to the front. So you'll get 2 times the natural log of x plus 4. All right, now we just have one more expansion because we factored this. So now this is going to use product to sum. And I get 1/3 times the natural log of x minus 2 plus the natural log of x plus 1 minus 2 times the natural log of x plus 4. Okay, and now the very last thing to do is let's go ahead and distribute that 1/3. I don't think we have to, but we'll do it anyways. So you'll get 1/3 natural log x minus 2 plus 1/3 natural log x plus 1 minus 2/3 natural log x plus 4. And there we have it. It's good time. Maybe I'll go back and rewrite all the rules I'm using. I'll do it after the video. Okay. So this page was about taking logs and expanding them and simplifying if possible. The next one is taking logs and condensing them into one single logarithm. Okay. So first up, you have 2 log base 3 of u minus log base 3 of v. So we know that since these are connected by subtraction, we're going to use the quotient to difference backwards. But before we do so, we have to get rid of this 2. So we're going to reverse power rule it. So this 2 has to go back on that u. I'll just leave that there. Why not? So this becomes log base 3 of u squared minus log base 3 of v. And now this is going to use the quotient to difference. So we can rewrite this as one single log base, saying log base 3 of u squared over v. And that's done. All right. Next one, log base 2 of 1 over x plus log base 2 of 1 over x squared. We have a plus symbol, which means we're going to use the product to sum, or sum to product, which means that we get to put these back as log base 2 of 1 over x times 1 over x squared. So log base 2 of 1 over x times 1 over x squared. And now just multiply the inside and you'll get log base 2 of 1 over x cubed. Okay, this should be it because we wrote it as one single log. But if it wants us to simplify more, you could also write this as log base 2 of x to the negative 3, which can also be written as negative 3 log base 2 of x. So this could possibly be an answer 2 if we wanted to super simplify. Okay, good times, right? All right. The next one, we are connected by subtraction. So once again, we're going to do quotient to difference, difference to quotient, since we're working it backwards. But the first thing before we do so, we got to get rid of that 2. So that's coming back on the x plus 1. So you'll get log of x squared plus 3x plus 2 minus log of x plus 1 squared. And now we quotient to difference this, and we will have the log of x squared plus 3x plus 2 over x plus 1 squared. Now, we should be able to keep going because we notice that this numerator is definitely factorable. So we could write the log of, that factors to x plus 1 times x plus 2 over x plus 1 squared. X squared, 2x, 1x, 3x, and 2. Where we notice that that x plus 1 cancels, that power of 2 cancels, and we get our final log of x plus 2 over x plus 1. Okay. going. All right, 1/3 log x cubed plus 1 plus 1/2 log x squared plus 1. So we see that these are connected by addition. So we're going to use the product to sum to product. But before we do so, that 1/3 has to go back there. That 1/2 has to go back there. So we'll get log of x cubed plus 1 to the 1/3 plus log of x squared plus 1 to the 1/2. Okay. And then, once again, we're connected by addition. So we can rewrite this as the sum to product, which means you'll get the log, I'm going to put a bracket here to be neat, of x cubed plus 1 to the 1/3 times x squared plus 1 to the 1/2. And I honestly don't think there's anything else we can do there. We could rewrite it as the log of the cube root of x cubed plus 1 times the square root of x squared plus 1. And that's as much as we can do. Okay. All right. Next one. Look at this. 3 terms. Subtraction, subtraction. All right. So we know we're going to use a lot of the quotient to difference here. But once again, before we do so, we got to get rid of that 3. And you got to get rid of that 2. We have to move them, right? So this means you'll get log base 5 of 3x plus 1 to the 3rd minus log base 5 of 2x minus 1 squared minus log base 5 of x. So we took those powers, put them back on top. And now you can work this left to right or right to left. Let's start by doing this left to right. Doesn't matter, you'll get the same answer. So first thing we're going to do is combine these two by the quotient to difference. So that should give me log base 5 of 3x plus 1 cubed over 2x minus 1 squared minus log base 5 of x. Okay. And then, once again, we quotient to difference that one. Difference to quotient, right? Quotient to difference, difference to quotient. Just know that we're reversing it. So I'll get log base 5, big bracket to be neat, of 3x plus 1 cubed over 2x minus 1 squared over x. And now you have a fraction over a fraction, because you can put x over 1 and multiply by the reciprocal. So that would give me log base 5 bracket. Maybe not a bracket anymore, but whatever. Keeps it neat. Of, because if you multiply by the reciprocal, that'd be 1 over x. So that would stay in the denominator. Okay, so then you'd get 3x plus 1 cubed over x times 2x minus 1 squared. close bracket. And there it is. Nothing else we could do there. Oh yeah, how do you check your work? Expand it back out, right? Let's look at that. If we expand it back out, do we get the same? Do we get the original problem? And let's see. I would have log base 5, since it's a quotient of difference, of 3x plus 1 cubed minus the log base 5 of x times 2x minus 1 squared. I would power rule this one. So you'd get 3 log base 5 of 3x plus 1. This one has to be product to summed, so that minus would stay out front, and you'd get log base 5 of x, not x plus, sorry, plus log base of 2x minus 1 squared. Then you would distribute that negative. I'll just leave that there because I'm going to erase it anyways. You get 3 log base 5 of 3x plus 1 minus log base 5 of x minus, and in the same move, I take this 2 and move it to the front, 2 log, I forgot my 5 there, log base 5 of 2x minus 1. Now, does this look like that? And the answer is yes. All right. So you can check your work by definitely expanding it back out. I recommend doing it because it gets you better at working with these properties. Okay. Oh, if you want to see it worked right to left, let me know in class. We can do that because you'll get the same answer. All right. Okay, moving on. So this is about approximating a logarithm whose base is neither 10 nor e. How do we approximate this log? Okay, well, if you remember from the last section, we take the log and set it equal to our favorite variable. So let's say we'll set it equal to x. And now, in order to solve this log, you have to convert it from log to exponential. So remember that the 2 gets raised to the x, and then you set it all equal to the inside of the log, which is 7. Okay. But now, we run into an issue here. Can 7 be changed into a base of 2? And the answer is no. Not unless we know what that x value is that makes 2 and 7. So now the only way to solve this is to apply logs to both sides of the equation. So what we're going to do is say log of 2 to the x equal to log of 7. So we compose both sides with logs. We can say we compose both sides with logs, or we apply logs to both sides. And now, by using logarithmic properties learned today, we can take this x and move it to the front by power rule. So that's what we're going to do. We will rewrite this as x times the log of 2 equal to the log of 7. And now all we have to do to solve for x is divide by the log of 2. And now we will get x equals log 7 over log 2. And then we'll punch it in a calculator. But we don't have to do that now. This is just showing you how to solve for x by converting from log to exponential and then composing with logs on both sides. Don't worry, there's a reason for this. I do have to show you option 2. So this works by composing both sides with a log, or this also works by composing both sides with the natural log. Either way, you'll get the same answer. So now I could say natural log of 2 to the x equal to the natural log of 7. And once again, by logarithmic properties, this x will move to the front. And we'll get 2 times the natural log of 2 equal to the natural log of 7. And all we have to do is divide by the natural log of 2, and we get x equals natural log 7 over natural log 2. And believe it or not, if you punch this in a calculator, whether using logs or natural logs, you're gonna get the same decimal number. I got time to show that, right? Okay, so I can say log 7 over log 2. And I'll get 2.807. I can also say natural log 7 over natural log 2. And guess what? 2.807. It's amazing, right? Okay, so that's just to show you that you'll get the same answer in the calculator no matter which log you use, the common log or the natural log. But the best takeaway from all this is that you really don't have to do this process anymore. You shouldn't have to do it, because what this whole process leads to is a new log formula called the change of base formula. So we say, if you're ever given log base A of m and told to approximate, then we know that by what we have done above, that log base A of m can become log m over log a, which is also equivalent to natural log m over natural log a. And we have proven that by what we've done above. So when we say approximate log base 2 of 7, by the change of base formula, this becomes log 7 over log 2. Exactly what we did there. Or this also becomes natural log 7 over natural log 2, what we did there. And that's all you need to do. No more of this process. If you know change of base, it makes life simpler. Oh, logs, you are so crazy. I know. But so fun. Okay. So now we will, I guess we'll be using the calculator on this. Approximate log base 5 of 89. So by using the change of base formula, log base 5 of 89 becomes log of 89 over log of 5. Or equivalently, it also becomes the natural log of 89 over the natural log of 5. Let me put parentheses just to be proper. And now we will approximate, so I guess it is calculator time. And I'll do natural log 89 divide natural log 5. Here's another type of input you could do. You don't have to use a fraction button. And I'll hit enter. And we'll do this to 3 decimal places, just because it's a logarithm. And I'll get 2.789. And that's the answer I get no matter if I use log or natural log. Okay. But now, for you TI users, TI-84 users who have the updated TI-84, you're in for a special treat. You don't have to worry about change of base at all. But I still recommend doing it because we don't want our calculators to do our work for you. Watch this special treat. You're gonna hit the math button. And I think you're gonna go to, where are you? Ah, there you go. So you're gonna hit the math button, and on the first menu, you're gonna scroll up and go up to log base. Look at this, log base. Oh, life is gonna get really easy here. Hit enter, and look at that. It says type in your log base and type in the number. We'll see log base 5 of 89 and hit enter. What do we get? 2.789. Oh my goodness. Life is easy. But remember, you still must use change of base. Just do it. Like I said, don't let the calculator do everything for you. Okay. And now this says approximate log base square root of 2 of the square root of 5 using change of base. So this means that log base square root of 2 of the square root of 5 by change of base becomes log square root 5 over log square root 2. And yes, we can type it into a calculator just like this. Or if you want to get crazier, we can go ahead and rewrite this as log of 5 to the 1/2 over log of 2 to the 1/2. And by power rule for logs, these powers come down. It's a beautiful thing. And you'll get 1/2 log 5 over 1/2 log 2, where your 1/2s cancel. And now all we have to type in our calculator is log 5 over log 2. And I'll just do that real fast. Log 5 over log 2. Or natural log 5 over natural log 2. No matter which way you go about it, you'll get 2.322. Woohoo, look at that. Okay. And now some fun log expressions. Definitely where we need to use the change of base. It says, what is log base 3 of 8 times log base 8 of 9? So this one, we definitely want to use change of base. So for log base 3 of 8, you're going to get log of 8 over log of 3 times log base 8 of 9 becomes log 9 over log 3. I didn't put parentheses. Okay. Sure, parentheses, 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 parentheses. And now we have the multiplication of two fractions using change of base. And now you see that your log, oh wait, sorry, that's not a 3. That should be an 8, sorry. And now you see that your log 8s will cancel, and you're left with log 9 over log 3, where for now, you can type it in a calculator, but I want to have more log fun. So log 9 can actually be changed into log of 3 squared over the log of 3. And by power rule, that 2 moves to the front, which means you'll get 2 log 3 over log 3, and your log 3s will, oh my goodness, sorry. Your log 3s will cancel, leaving you with 2. The answer you could have got a long time ago by typing that in the calculator. It's good times, right? Logs are insane. I love them. Okay. Now another one to simplify by using change of base. Oh boy, look at this. So simplify e to the log base e squared of 16. Okay, so this part definitely has to be simplified. We can't use that property in the beginning because yes, the bases are the same, but this base is being raised to the second. So we have to simplify more. So let's go ahead and first look at log base e squared of 16. And by change of base, I want to write that 16 lower. There we go. By change of base, you'll get log of 16 over log of e squared. Okay, so what's going to happen here is we know that this 2 will come to the front. But we also know that 16 can be written as a base of 2 or 4. So let's see how this works out for us. So let's go ahead and just rewrite 16 as 4 squared. And there's a reason I'm doing this. So you could have went another way and wrote it as 2 to the 4th. But I'm writing it as 4 squared. And this becomes 2 log of e. And now, since this is 4 squared, that's ugly, 4 squared, this 2 will also come down. And I'll get 2 log of 4 over 2 log of e, where my 2's will cancel. And now we are left with log of 4 over log of e. Now remember how I kept saying that all log properties are reversible. So now we're going to do a reverse change of base, right? A reverse change of base. So remember, change of base is log base a of m is equal to log base m over log a. So this means that whatever number is in the denominator is going to become the base. Whatever number is in the numerator is going to become the number that we're taking the log of. So we're going to reverse this. Oh boy, right? So let's write it the other way. I'm going to say log m over log A becomes log base A of m, reverse change of base. That means that this becomes log base E of 4. We just reversed it. All right, but we're not done because that was just the exponent. So now we come back to the original problem, and now you get E raised to the log base E. Stop writing ugly. E raised to the log base E of 4. And now we can use that property in the very beginning. This base is the same as that base, which means the bases will cancel and leave us with 4. Oh man, good times. All right. So, yeah. I think those are all the log properties we know. Change of base, power rule, product to sum, quotient of difference, all that good stuff. Okay. Now the next page is a fun one. It's called Being Real Extra with Logarithms. Let's use all the log properties today to simplify these expressions. We're being really extra. Okay, so look at this first one. Log 3 times log 4 times log 5 times log 6 times log 7 times log 8. It wants us to simplify this expression, and the only way we can do that is by using change of base on all of these. So this would become log 3 over log 2 times log 4 over log 3 times log 5 over log 4 times log 6 over log 5 times log 7 over log 6 and times log 8 over log 7. Oh, good times, right? And now we have multiplication of fractions, and we see that cancel, 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 cancel. Look at that. And what we're left with is log 8 over log 2. And you could do reverse change of base on it, or we can have more fun and say that 8 is also 2 cubed over the log of 2, which becomes 3 log 2 over log 2, which cancel, and our final answer is just 3. Oh my goodness, so much fun, right? It's too much fun, too extra, okay? All right, so this next one is called a proof. We're gonna prove this identity. It says show that log a of the square root of x plus square root of x minus 1 plus log base a of square root of x minus square root of x minus 1 is equal to 0. So this is called an identity, and we want to prove it. So this means we start by using one side. Whenever you prove an identity, so this is called an identity. And whenever you prove an identity, you choose one side. You either choose the left or you choose the right. And when you prove identities, you always choose the most complicated side. And that happens to be the left side. So we're going to say proof by left side. So we start with log base a of the square root of x plus square root of x minus 1 plus log base a times the square root of x minus the square root of x minus 1. We don't set it equal to 0 because we're trying to prove that this left side is equal to 0. So first thing we notice is that these are connected by addition. So we get to use the product to sum. So say log base a, put a bracket there for neatness, and you'll get square root of x plus square root of x minus 1 times the square root of x minus the square root of x minus 1. And now what we're going to do is FOIL. If you FOIL, you should get x, the middle terms cancel, and you should get x times x minus 1. Which means that this becomes log base a of x minus x plus 1, which becomes log base a of 1. And if you scroll back to the very first page, the log of 1, no matter what the base is always 0. There you go. So we have proven that that whole expression on the left side is equal to 0. Whew. That's how you do identities. You'll see those in pre-cal. Okay. Oh man, there's still more. Okay. So once again, let's see, show that the natural log of 1 plus e to the 2x is equal to 2x plus the natural log of 1 plus e to the negative 2x. Okay, we got this. So let's see. Of course, this is an identity, so we're going to start with the right side. This is another identity. So we're going to say proof by proof by right. So we start off with 2x plus the natural log of 1 plus e to the negative 2x. And we are going to fix this inside. And when I say fix that inside, we're just going to rewrite it using exponential properties. This becomes 1 plus 1 over e to the 2x. And then what we're going to do next is get a common denominator. You're going to put this 1 over 1 and multiply by e to the 2x. So that should give you 2x plus the natural log of e to the 2x plus 1 over e to the 2x. And now, by logarithmic properties, you have a quotient on the inside. We can expand this to the difference. So you'll get 2x plus the natural log of e to the 2x, e to the 2x plus 1, minus the natural log of e to the 2x. And now, continuing this proof, you'll get 2x plus, nothing can be done here, e to the 2x plus 1. But on this natural log, we can use power rule and bring that 2x to the front. So you'll get minus 2x times the natural log of e. And then you get 2x plus the natural log of e to the 2x plus 1. And remember that the natural log of e is equal to 1. So this means that you get just negative 2x, and then your 2x's will cancel, and you get left with the natural log of e to the 2x plus 1. We have just proven that the right side is equivalent to the left side. Good times, my goodness. These are fun. Probably more fun for me, right? Okay. Last one. If f of x equals the log base a of x, show that f of 1 over x is equal to negative f of x. So this just says take 1 over x and plug it in for x into this function, and let's see what happens. So f of 1 over x would give me the log base a of 1 over x. And now if I expand this by quotient to difference, you'd get log base a of 1 minus log base a of x. But remember that log base a of 1 is 0. So you end up with 0 minus the log base a of x, which gives me the negative log base a of x. Which means that, if we look at the original problem, it says show that the f of 1 over x is equal to the negative f of x. Well, if f of x is the log base a of x, then this must be negative f of x. Hey, look at that. And that's all she wrote. So, your biggest takeaway here is know how to work the formula, no change of base, and know how to work the 3 main properties. Right here. Product to sum, quotient to difference, and power rule. Know that all these log properties are reversible, and just know how to work them. The other ones, it's very good to know. Like I said, if you need that help, reference this or just pull out the calculator. Okay, that is it for log properties. Crazy, crazy section, I know, but you just gotta have fun with it. Okay, well, see you guys at the next one.